Hi you guys, Mrs. Valdivia here. So we're gonna go into chapter 5, which is chemical bonds, and let's get going. So this is a very long chapter. It's very detailed, and then there's still things that we need to cover that are part of this chapter. But the lecture here on the PowerPoint doesn't cover it too much. So I'll be making some other little lectures on it. So please make sure to watch them and showing you how to do certain things. Okay. So chapter 5, chemical bonds. The first thing we want to note is Lewis symbols and the octet rule. Things to note about this one is where your valence electrons are at and how easy it is to figure out your valence electrons by looking at a periodic table. So let's look at an example here. If you follow here with me, let's look at nitrogen. All right, so nitrogen on the periodic table is located in group 5A or group 15. 15 only if you count the 10 transitional metals right here, if you're going to count those. Usually we skip them because when it comes to valence electrons, the only valence electrons you're going to have are from the S, which is this one, and the P block, which is this one, right? So if we recall from our last video, we have S block, P block. All right, so we're only going to count those as our outermost valence electrons that only come from the S and the P block. Okay. So you're going to have 1 from group 1A, 2 from group 2A, 3 from group 3A, 4, and 5. So nitrogen has a total of 5 valence electrons. Why? How? Please explain. Don't just show me the trick. Awesome. I'm glad you asked. All right. So the S block right here can hold up to 2 electrons. 1, 2. Remember, you hold 2 electrons in each orbital. The S is that beautiful spear-like shape, so 2 electrons are floating in there somewhere. The next sublevel, right, is the P sublevel, and the P sublevel has a total of 3 orbitals. We have 1, 2, 3 orbitals. So we could fit a total of 6 electrons in the P sublevel. In this case, for nitrogen, it only has 3 electrons that are going to try to fill that P sublevel. If you count them together, 2 plus 3 is equal to 5. 5 valence electrons. You're also welcome to draw the atom out. And if you draw the atom out, you will end up with 5 valence electrons in the outermost shell. All right, so that's kind of cool. So now you guys can know that if I say, hey, how many valence electrons do noble gases have? You're going to go to the noble gas, which is the last column, column 8, and you're going to say, oh, it has 8. All right, this is called satisfying the octet rule. It's having 8 electrons in your outermost shell. Every atom wants to have 8 electrons in its outermost shell. And it's going to do this by either losing electrons or gaining electrons. Okay, so the Lewis dots. The dots represent the valence electrons. That's basically it. So every time you see an element with a dot, it's saying it has 1 valence electron. So lithium and 1 valence electron. Beryllium is going to have 2. Boron, 3. Carbon, 4. Right? And just like we were doing in our atom, you want to make sure that those electrons are separated in a T-like fashion. So different ways to remember it is you could say north, south, west, east, or you could do your crucifix prayer, or you could say you have to have it on a T. Either one of those ways, but make sure that they are nice and lined up, making those 90-degree angles between them. Okay. So if I get a little pen, and if I'm like grading papers or something like that, right, I should be able to, and you should be able to put a straight line connecting 2 of your valence electrons together like that. So they should be able to connect, okay, and create a nice little house, like a square house. The reason why we do that is because when we start putting the atoms together with other, or elements with other elements together, right, or atoms with other atoms, whichever one you want, they need to arrange themselves in a way where we could see what formation it's going to make, what shape that bond is going to produce. So octet role. An atom is stabilized by having its valence energy level filled. All noble gases already have a full octet. They're already full, so they don't really want to gain or lose electrons. Okay. And the other atoms, they're all going to gain or lose electrons. And remember, when you gain or lose electrons, you become an ion, right? So if you're gaining electrons, okay, so for example, fluorine is going to gain 1 electron. Oxygen will gain 2 electrons. Nitrogen will gain 3 electrons. And carbon, well, carbon is tricky. Carbon could either gain 4 or lose 4, right? So at this point right here, which is our center, right? This actually divides whether something's going to gain or something's going to lose electrons, okay? And sometimes our metals, well, they like to share their electrons as well, right? So the type of element you have is also going to depend if something's going to share or take electrons. Okay? So for example, beryllium is going to give away its electrons. So it'll give away these 3 electrons. That was boron. This one's beryllium. Beryllium will give away 2 and lithium will give away 1. So when it gives away 1, it's going to make a +1. Beryllium will make a +2 charge. Boron will make a +3. Nitrogen will make a -3. A -2, a -1 charge. These ones right here are not going to make a charge because they already satisfy the octet rule. Carbon is right here in the center. It's in the middle. So it's either going to gain 4 or lose 4, right? The -4 is actually gain 4 and the +4 is lose 4, right? Because it's the electrons that we're talking about. Okay, so we already know that atoms have overall charges. The transitional metals right here, you'll notice that these ones have more than 1 charge. And so do our tin and our lead. They also have more than 1 charge. Okay, no easy way of doing that, but either you can memorize it, or if a name is given to you, which we're going to go over naming, you could figure out what charge it actually has. Oh, cool, I can push that. All right, so if we recall, if you're a positive ion, you're so positive, you're called a cation, right? That means you're a main group element, you're a cation, you're going to be losing electrons, okay? You're gonna lose electrons, and you're gonna lose them until your energy level is filled. So that means you're gonna probably go down 1 energy level in order to satisfy your octet rule. So let's take a look at this one. Okay, here neon is a noble gas. This is neon, and neon has a full octet. Okay, sodium. So neon, by the way, is a 2p6. Sodium right here is a 3s1. Okay, configuration. So you can see right here. All right. It has 11 electrons. So that means it only has 1 electron in its outermost shell. Only 1, right? It doesn't like that. It wants full octet ready to go. Atoms and humans and everything in nature, we always take the easiest path possible. The easiest path means that I'd rather lose 1 than gain 7. Okay? It's not about losing or gaining. It's about what takes the less amount of steps. Okay, so it takes less steps to lose 1, and it takes more steps to have to gain 7. So sodium's like, nah, go ahead, take my electron. I'll gladly give it to you. All right, so it shares the electron, and its electron then goes away. When that happens, you'll notice no more electron is here, but it now has a full octet because this right here is now its new outer shell. So that's the new outer shell. Okay. And that is now your bonding shell with your bonding electrons. Okay. All right. So let's go ahead and look at sodium and show the example of what we just saw using the Lewis dot symbols and its configuration. So sodium is going to lose one electron. It attains the same electron configuration as neon when this happens. Note that the electron doesn't just disappear, doesn't disappear into thin air, nothing like that. So here's sodium, okay, with its one valence electron. It starts to lose an electron. So here's sodium now, it has a +1 charge, but we also have to indicate that electron. So you can't forget about it, right? Because where did it go? Where is it? And how many do we have? We have, we have one electron. Okay, this is our electron that's going to now be shared with a different atom. Okay, so as a general rule, all alkali metals, that's metals that are located in group 1A of the periodic table, that first group, lose one electron and they all form a +1 ion. The group next to it, 2A, the alkali earth metals, are going to lose 2 electrons and they're going to form a +2 ion. Okay, and that's our example of a group 2. This is magnesium. Magnesium is a 3s2. It's going to lose 2, and you're going to get magnesium with the +2 charge plus 2 electrons that are available for bonding. Okay, transitional metals also form cations. I hope by now you've caught on that all metals start to form cations, right? So metals tend to give up their electrons, okay? Transitional metals typically form ions having a charge between a +1 and a +4. These charges can range. They can have multiple charges. The metals in the lower part of the P block, these ones right here, okay, they also behave in that way as the transitional metals do. So it's important to note those, right? That this is going to be tin, can be a tin 2 or a tin 4, and lead could also be a lead 2 or a lead 4. Right? Zinc and silver are the only 2 transitional metals that have a fixed charge. Okay, so every time you see zinc and silver, you're going to know that they have a fixed charge. That means their charge doesn't change. It doesn't depend on anything. Okay, so now let's go into our naming of our cations. Okay, metal cations have the same name as the neutral metal. So example, sodium with a +1 charge is just going to be called sodium. Magnesium with a +2 charge is just going to be called magnesium. Okay. We do have some names that used to have a Latin name associated with them. So if we look at iron, you notice that iron and the element symbol do not match, and that's because iron used to be called something else. It used to be called ferrous. And if you had iron with a +3, it was called ferric. Okay. Our modern name, before we go into those, so then we look at copper, we're going to have cuprous and cupric. Cuprous and cupric. Okay. These were the older names associated with them, but some people were getting confused and whatnot, and it's easier to just represent these ions with the symbol and the number attached to them so nobody gets confused. Okay, so now ferrous, instead of saying that, we're going to write it down as an iron with the Roman numeral 2 inside parentheses. Ferric, which is iron with the +3 charge right here. Well, guess how you're going to do that? Yep, iron, parentheses 3. Okay. Cuprous. So with cuprous, same thing. You're going to write copper, parentheses 1. Or cupric, copper, parentheses 2. Okay. It just helps us know which element we're talking about without being confused, especially if we're talking to someone from a different country. So if we start naming the following, the first one Ag, remember Ag is silver and it has a fixed charge, so therefore it's just silver. Lead has a +2 charge. It's not fixed. It could either be +2 or +4. So I think we're going to be naming that lead with a parentheses number 2 or Roman numeral 2. And the same thing with lead with a +4 charge, lead with Roman numeral 4. Most nonmetals fulfill the octet rule by gaining electrons. Those are our anions. So if we look at these ones, these are our common anions. There's not that many of them. There's more metals than there is nonmetals. All right, so here we go. Here is fluorine. Fluorine is a nonmetal and it's going to gain electrons. So that's why you see fluorine plus an electron. It's gaining that electron. So now you're going to have fluorine with a full octet. Okay. Oh, there we go. All right. So everything in column 17 gains 1 electron. So 7 takes 1 to make it to 8. So it's a +1 electron, giving it a -1 charge. Oxygen is in group 6A. It has 6 valence electrons. It needs 2 more to reach the octet. So it's going to gain 2 electrons. Right? Here's the example of oxygen being shown. So in oxygen, it gains 2 electrons and it now becomes oxygen with a -2 charge, so an oxygen ion or an oxide ion. So one of the things about anions is that unlike cations, where we keep the same name, like sodium, right? We would just say sodium ion. We're not going to keep the same name for our anions, okay? The names for our anions is going to change. So we're going to see that differently. So for example, chlorine is going to change to chloride. Oxygen is going to change into oxide. Sulfur is going to change into sulfide. And nitrogen will change into nitride. All right. Oops. One second. All right, guys, so this little thing slightly froze, but we'll figure it out. Dun, 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 dun. Okay, let's see. All right, we're just going to use this. Okay, so polyatomic ions are groups of atoms with a charge associated with them. So all that means is that you have an atom with um, more than one element connected to it, right? And you're going to be making a polyatomic ion. So that's all it is, a group of atoms with a charge put together. This chart represents the most common polyatomic ions, okay? You'll notice you have ammonium, you have sulfate, SO4, right? So if you put a hydrogen like this in front of it, you're going to have sulfuric acid, right? Yeah, so these most common ions. Okay. So polyatomic ions, group of atoms with a charge. Then you have oxyanions. That means they contain oxygen, usually named as an element. So you'll say the element's root word, then you're going to end it with the word 8. So for example, carbon is going to be carbonate. Okay. Um, yeah. If you have phosphorus, phosphorus is going to be phosphate. So there's phosphorus, and phosphorus turns into phosphate. So let's look at another one. Okay. You can have more than one oxyanion. So in this example, we're going to look at nitrogen. Okay, you could use the suffix of ate to indicate the ion with more oxygen atoms present to it, and the suffix of ite to indicate the ion with fewer oxygens present in it. What does that mean? Actually, this is how I remember it. I always say, oh, I ate too many oxygens. Or I ate, man, I wish I ate more. So if you ate more, you're going to end in ate. If you had less, you're going to end in ite. Ite, why aren't you sharing? Okay. So nitrate and nitrite. Finishing up and taking a look at a couple more, you're going to have chlorate, chlorite, and then you'll notice that these ones here are more extended than the others, so they're going to be perchlorate and hypochlorite. Okay, so per meaning above and more of, and hypo meaning less of. All right, that's again ions to know. Okay. So ionic bonds and compounds, that's the next thing we want to kind of try to cover, is going to be the ionic bonds and compound section. Okay. So okay. When ionic bonds are starting to form, they're going to be joining together. Okay. So opposite charges are going to join together. When positive and negative charges come in contact together, it's like they create stickiness, right? They stick to one another. This is similar to a forced attraction between oppositely charged ions. So it's like a forced attraction, okay? And ionic compounds are made between metals and non-metals. So that's something to note, is that you're going to have a metal, which is your positive cation, and you're going to have a non-metal, which is going to be your negative anion. And these form together to create an ionic bond. So a lattice is just basically an array of positive and negative ions being combined together until you make this nice little lattice. So you can start combining them. They have a structure, right? And this structure just tends to form a lattice of everything packed together. So it's a 3D kind of structure. Now let's go into chemical formulas. Okay? So chemical formulas, they represent the composition of compounds, and we use the chemical formula to indicate the type of amount of each element present. We represent ionic compounds using a specific type of chemical formula known as empirical formulas. So the empirical formula is the smallest whole number ratio of atoms, right? Like H2O is the smallest whole number ratio of it, but that's more like for covalent. In this case, we're talking about ionic, and we could use something like NaCl, sodium chloride, right? So sodium chloride, I'm not going to say I have Na23 and Cl23, because I can't count that many of those molecules. They're so small. So we basically write everything in its empirical formula status. All right, let's go into ionic compounds. and how do we put them together. So this one says, write the formula for a compound composed of potassium and sulfide ions. So here's my potassium. I had 1 plus an S2. Okay. Potassium has a +1 charge and sulfur has a -2 charge. I need these to come together. Okay. When I put two potassiums together, I'm going to get a +2 charge. Your positive charges must equal your negative charges unless there is an ion present in the formula. And you're going to know there's an ion present because it's going to have a plus or minus next to the top of that compound that you see. When we put these together, we're going to need 2 potassiums to 1 sulfur, K2S. Right? So we're going to write the compound of something composed of calcium and nitrate. Okay? So calcium plus nitrate, you'll notice that calcium has a +2 charge, nitrate has a -1 charge. So you're going to need 2 nitrates in order to balance out with 1 calcium. You'll end up with calcium nitrate. All right. I'm going to skim through this one. Actually, no, let's go through it because you're going to be using the parentheses. All right, so we're going to use aluminum and sulfate ions. You'll notice that aluminum's a +3 and sulfate is a -2. So how are we going to do this? Well, if you crisscross these, right, you're going to need 3 sulfates for every 2 aluminums. And you're going to write this as aluminum 2 and then sulfate with 3. You're not going to say those out loud. You're not going to say aluminum 2, sulfate 3. You're just going to say aluminum sulfate. So the next one right here is just naming ionic compounds. Okay, so with this one, the first one, remember if it's a cation, it's going to keep its first original name. So sodium, and then the second name connected to it is just going to be chloride. Magnesium, chloride. Magnesium, sulfate. Right, let's look at these copper ones. Remember, copper has more than 1 charge. So the first one, copper, is going to be a +1. And this one, copper, is going to be a +2 for the bottom one. When you write the charges down, make sure that you put it in parentheses and then put the number next to it. This is the charge number. This indicates that copper has a +1 charge in its ion system. Right? In this case, copper has a +2 charge in its ion system. I'm going to skip these. We're going to be going into covalent bonds. Actually, yeah, no, we'll go into covalent bond. So electrons are shared between 2 atoms in a covalent bond. Ionic bonding, they weren't shared. Excuse me. Excuse me. Ionic bonding is a little bit more different. In this case, you're taking away electrons or giving electrons. You're completely giving it away. Covalent bonding is the sharing. So sometimes you're going to have equal sharing or you're going to have unequal sharing. In this example, we have equal sharing of our covalent bonds. Okay, so covalent bonds, and how does it work? So first we're going to have this diatomic element of fluorine. Okay, so fluorine has 1 valence electron available to it. And when they combine, these 2 electrons are going to actually combine together, okay, to form a single bond. Now, I usually like to do work and I'll show that they're going to go here and they're going to meet up here, right? That's where they're going to move. So they're going to walk away and they're going to be shared. And then you'll see me put my electrons one up, one down. You could also do side by side. That is okay as well. Okay. So, but this gets cleaned up, and when it gets cleaned up, um, it's going to look like this, or with a solid line. And that's called your Lewis structure, right? Quite simple. Just make sure you connect only the lonely valence electrons. Do not connect electrons that are already paired up together. Only the lonely ones. All right, we went over diatomic. All right, so covalent compounds fulfill the octet role by sharing electrons. And not all the time is that sharing equal. Okay? Sometimes the sharing is going to be unequal. Okay? So Lewis structures are going to depict the arrangement of the valence electrons in the molecule or the polyatomic ion. So in this case, oxygen has 4 unshared electrons and 2 covalent bonds between the unshared and the shared electrons. Oxygen has 8 electrons in its valence level and fulfills this octet. What does that even mean? Okay, so what I'm saying here is that oxygen has 8 electrons total. It's going to have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so oxygen has 8 valence electrons surrounding it. And so it's fulfilling the octet rules. All right, in this structure, how many electrons does nitrogen atom share through covalent bonds? How many valence nitrogen electrons are not shared? And does this nitrogen atom have a complete octet? All right, so first let's start counting to see if there's a complete octet. All hydrogens are good. They fill with 2 maximum. And nitrogen's going to fill with 8. I have 2, 4, 6, 8. So nitrogen has completed the octet rule. How many valence electrons are not shared? So how many valence are not shared? That is 0. They're all shared together. Okay. Let's see. Okay, molecular formula gives you the number of atoms inside the molecule. All right, we already know that covalent bonds all have complex like structures. Okay. Okay, so now we're going to go into naming our binary covalent compounds. So in naming these, it's really quite simple. Okay, covalent compounds containing only 2 elements. Okay, are called binary covalent compounds. These compounds are named in a manner that is similar to ionic compounds. Similar, but there are some key differences. Okay, so let's look at lead chloride and lead chloride basically. So I have lead chloride with a 3 and lead chloride with a 5. Um, one of the questions is, why am I not naming chloride first? Why do I name chloride second? Well, it's because you're always going to start and name with the element that is furthest to the left. Okay? The element that's furthest to the left. Okay, that's the one you start with. And you end with the one element that's furthest to the right. Okay, because covalent bonds form in many different ratios, we're going to use a prefix before each element to indicate the number of atoms that element has present in it. Okay, so we're going to name these, and you're going to see what this one is going to be called. So this first one, okay, is phosphorus trichloride. So phosphorus, which is the name, tri, and then chloride. The second one is going to be phosphorus, again, pentachloride. Penta stands for 5. If you weren't sure, you could always look right here. Right. Pent or penta, right? So remove A if anion belongs with a vowel. You're gonna remove the letter A, okay, to identify, well, which one is it gonna be? Is it gonna be pent or is it gonna be penta? Right? Where's my mouse at? Okay. So again, example, we have nitrogen dioxide. And in this case, you'll notice that the first name has a name to it. No worries, nothing big, just saying dinitrogen tetraoxide or tetroxide. Okay, one of those two forms will work very, very well for me. All right, a little quick summary. Covalent bonds, atoms share electrons. Covalent bonds form between nonmetals. Most covalent compounds form discrete molecules. Um, and we describe molecules using the Lewis structures and molecular formulas. We also know that naming binary covalent compounds and leftmost element comes first, the rightmost element comes last. And prefixes indicate the number of atoms present. Okay, so let's look at this one here. We're almost done with our PowerPoints, just a couple more slides to go. All right, so we want to distinguish between ionic and covalent bonds. What is the difference between them? Covalent bonds share electrons. Simple. Covalent bonds share electrons, and covalent bonds are formed between non-metals only. Non-metal plus a non-metal. They usually form molecules and they have molecular formulas. An example of a covalent bond is sugar. Sugar is a covalent bond. It's like C6H12O6. And then you have ionic bonds. Ionic bonds are oppositely charged ions that get attracted together and form. Um, they create formula units, and we represent them using empirical formulas, which is the lowest ratio possible, and they create lattices. Okay? So lattices is basically a positive and negative ion stacking up on top of each other. So we have limestone and we have olive oil right here. Just kind of like looking at them and figuring out what are they composed of and what can it be. So limestone is composed of calcium carbonate, and olive oil is actually a combination of carbon, hydrogen, and oxygen. And we want to figure out what their properties are, right? Well, the first thing we need to know is it covalent or is it ionic? Limestone right here is calcium carbonate. Calcium is a metal. Carbonate is a polyatomic ion. So we have metal plus non-metal. That's going to be an ionic compound. Olive oil is carbon, hydrogen, and oxygen combined together. Those are all non-metal, so therefore it's going to be non-metal plus non-metal, a covalent compound. Okay, let's quickly identify these as covalent or ionic. We have metal and non-metal. Okay, metal plus non-metal is ionic. We're gonna have here no metal and non-metal. Sorry, excuse the typing here. So this one is gonna be covalent. I'm just gonna put a C for covalent. You have metal and a non-metal combined together, ionic. And here you're gonna have non-metal plus non-metal, which is gonna be covalent. All right. Oh, and I guess they gave the names of these as well. Okay. All right. Let's see where this leads to. Okay. So we're gonna go quickly into aqueous solutions as they relate to our ions. How ionic and covalent compounds differ inside of some aqueous solutions. Okay, so remember, aqueous just means a homogeneous mixture dissolved in water. Okay, soluble means able to dissolve, so it's soluble in water. You can dissolve it in water. So in this example, we have pure water and some sodium chloride inside of the water on the next one. What does this mean? Well, go ahead and take a look at the light bulb that's on top. And I want you guys to notice when we go from water to sodium chloride. Remember, sodium chloride is an ionic compound. And ionic compounds conduct electricity. Okay? So they form an electrolyte solution, and this electrolyte solution conducts electricity. So that's why the light bulb is able to turn on. So look at the different structures of each one of these. Okay, when ionic compounds dissolve in water, the positive and negative ions are pulled away from each other, and they get surrounded by the water molecules. So here's the example. Okay, your positive and negative ions, you're going to combine them in water, and next thing you know, you have positives and negatives floating around inside of the water on their own. So this is called dissociation. They dissociate from one another. They pull apart. Now we're going to go into our acids. Although most covalent compounds do not form ions when dissolved in water, there's one very important exception to this rule. Okay, so that's going to be our acids. Acids are covalent compounds that produce hydrogen ions in aqueous solutions. Most acids contain a covalent compound between hydrogen and a species that can form a stable anion. When dissolved in water, the bond breaks to produce hydrogen cations and a corresponding anion. Let's go ahead and look at this one. Hey, we're assuming that these are in an aqueous solution, so we're going to ignore the water for now, at least inside of the chemical equation, because we already know it's telling us that it is in water. When hydrochloric acid breaks apart in its water, you're going to get its positive on its own and its chlorine on its own, its anion on its own. Let's look at nitric acid. It's going to break apart. Hydrogen, which is the positive end, okay, is going to break apart from the polyatomic ion, which has the negative end. So the common acids that you're going to see are hydrofluoric, sulfuric, nitric, acidic, carbonic, hydrobromic, okay? Acids are corrosive, meaning they destroy many substances, including metal surfaces and your clothing. They can also cause severe burns to the skin and should be handled with care. So when you're in lab, make sure that you wear long pants, you have your goggles on, you have closed-toed shoes like tennis shoes, and nothing fluffy or full of but yeah, fluff, I guess, and some gloves. Okay, you don't want to burn your skin or anything like that. Binary acids are basically acids that are made from uh, two elements, so hydrogen and fluorine, hydrogen and chlorine, those kind of things. These are the most common ones: hydrofluoric, hydrochloric, hydrobromic, and hydroiodic. You'll notice that we're adding the word hydro to all of these. Okay, hydrobromic, hydrochloric, hydroiodic. And at the end of them all, we're also ending with the word ick. Icky, icky, icky. That is some hydro-ickiness. Okay. Oxyacids form between hydrogens and some oxygens. Okay. And one thing to note is that oxyacids are compounds that dissociate to form more hydrogen and some oxyanions. The two rules for these ones are this: if the anion ends in ate, name the acid by changing the suffix to ic. So example would be our nitrate. The corresponding acid, HNO3, is going to be called nitric acid. So here we go. Oh. Nitrate is going to become nitric acid. CO2, which is our carbonate, is going to become carbonic acid. Okay? And all we're doing is adding that H to it. Okay. So acids formed from sulfate and phosphate deviate slightly from the rules from above. Okay, sulfuric acid is not called sulfic acid. It is actually called sulfuric acid. Similarly to the H3PO4, it is not phosphoric acid, but it's going to be called, it's not phosphic acid, it's phosphoric acid. Okay. So those are just some two exceptions to the naming. Okay. Okay. If it ends in ite, it's going to change into aus. Right? If it ends in ite, it's going to change into aus. So the other one, it ended in ate and it changed into ick. And now it's going to end in ite and it's going to change into an aus. Chlorite, chloraus. A quick little summary of our ions. Ions form electrolytes when dissolved in water, and acids also form the electrolytes when dissolved in water, and that is because they form hydrogen ions. All right, you guys, that ends our chapter here. Remember, I'm going to add more videos to talk about a couple more things that weren't necessarily covered here that we had to shorten up. So we're going to talk about shielding effect, periodicity, and a little bit more on our Lewis dots and formula charges and whatnot. Okay, enjoy.